Good morning. Today we will see the lecture number 2 of the module Robot Dynamics and Control. First we will see what we have already seen in the last lecture. So this is a recap of the last lecture. First is we saw what is the motivation, why we need to study robot dynamics and control. Then we saw some fundamentals about the robot dynamics. Okay. In particular, we studied the Lagrange formulation, and we went through one example, actually several examples, one example of the robot manipulator to actually see through how the Lagrange formulation can be done. And then we saw briefly how to use the Newton's method for formulation of the problems of robotic manipulator. So any task that you carry out for the robot has to be done with the understanding of dynamics and control. Okay, especially this becomes important when you are talking about robots which are working at a fast speed. Okay, when robots are working at a slow speed, then the dynamics will not have a lot of importance. It will have importance, but it will not have a lot of importance. But when you talk about robots which are working at very fast speeds, you want higher performance, then the dynamics and control, they become complicated. So you need to have a fairly good amount of understanding about these issues. Now in the today's class, what we are going to see is the general procedure. We have seen a procedure in terms of one of the examples yesterday. So we will generalize this procedure to get the dynamics of robot manipulator, and then we'll go on to some introduction of control, like some fundamentals of control we'll understand. Okay, so this procedure that I'm talking about is already like we have seen yesterday, but now we want to make it more general for the cases having like a general configuration of a robot manipulator. So we have seen this for 2R manipulator. Okay, we studied the Lagrange formulation, we studied this procedure for 2R manipulator, and now we want to generalize it. So how do we do that? So first let me recap about the dynamics. The basic dynamics question that we again raise is, given the forces and torques on the manipulator joints, how will we find angular history or history of joint angles? So you basically are interested in getting the differential equations of motion for the robot manipulator. Okay, and we did this by using Lagrange formulation yesterday, and now I'll give you a generalized procedure that you should follow to get these dynamics. Okay, so this is a very important kind of a procedure that you will follow to get robot dynamics. Okay, first thing, you have to set up your configuration right for robot, and then perform kinematic analysis. By kinematic analysis, I mean basically the velocity analysis. Okay, then this velocity analysis, you have to use it for finding out kinetic energy. And you remember what expression we use for kinetic energy? This is basically the expression. And then you can see that this Vc is basically a velocity of Cg of the link that you are talking about, and then omega I, this is this term basically is angular velocity, omega I, and the kinetic energy because of the rotational part. Okay, now this can further be given by the Jacobian multiplied by your generalized coordinates. So this Vc is a translational velocity of the link, which is given by Jacobian in the translational case, multiplied by your generalized coordinate dots. Okay, and then omega I here is given by this formula. This is a Jacobian for omega I, Now important thing to note is that your inertia is in the link reference frame. Okay, typically when you have a body attached reference frame, your inertia parameters are known better. Okay, so they are constant in the body reference frame. If you transfer them to a base reference frame, then inertia parameters will change because it will involve the rotation matrices. So we want to avoid that. So here this link, the inertia is expressed in a reference frame which is attached to the link. Hence you have to introduce this rotational matrix over here to take care of its transformation. Like, see the transformation of omegas to the link reference frame. Okay, you understand that? Because you cannot multiply here omega in one reference frame and I expressed in other reference frame. You have to have all the three expressed in the same reference frame. So your omega should be in the reference frame which is same as the reference frame of I. Okay, this is an important thing, very important understanding. But see, the thing is that since this is the energy, whether you express in the like omega the link reference frame or in the base reference frame is going to remain the same. So since omega I is measured in the link reference frame, you have to multiply it by this R matrix. This is a rotation matrix transforming from base through the link reference frame. Okay, next we'll move to the next step to express this kinetic energy in this form. Now remember that this is a total kinetic energy. Okay, this is kinetic energy of all the links taken together. This is not just a kinetic energy of one link. You can see that there is a summation over here. Okay, this kinetic energy is of all the links. Okay, so this kinetic energy you have to express in this form, separating out this D matrix. Okay, so you get this D matrix from here and corresponding elements D I J of this D matrix. Next you find this potential energy. So this is a RC is a link CG. Okay, the coordinate of the link CG, and then this G is a gravity vector expressed in the base coordinate frame. Okay, Mi is link mass. Okay, so summation of these over all the links will give you potential energy of the. Okay, next we will consider the Lagrange equation and apply it to this system. Okay, using this potential energy, and now we will use a simplified form of the Lagrange equation. Okay, so this simplified form we use D directly, which we have gotten from the kinetic energy of the links, and then we will estimate the C parameters using again the D terms and this formula. Okay, we derived this formula in the last class. Okay, we will use this formula to get your C matrix, and then this G matrix here is different from the gravity vector. Okay, this G vector is given by differentiating the potential energy terms. Okay, and then this tau is generalized force acting in the direction of the generalized coordinate. So tau is a generalized force acting in the direction of generalized coordinate. Okay, now this tau may contain your damping terms also. So you should remember, like if any forces that you have to consider, external forces other than your input, then you have to consider them in the tau. Okay, so in general, damping forces, friction forces, they will show up in this tau term. Okay, next we will see how this equation looks like. It is a second order ordinary differential equation. You can see there is a double dot over here, and there are n such equations for n link manipulator. So I have expressed this in a vector form already for all n links. Okay, so you will in general get 2n order ordinary differential equation. This is ordinary differential equation. There are no partial derivative terms, and it can be solved for these generalized coordinate QIs. Okay, how will you solve this? You can solve it usually, if it is in the simple form, you can solve it by doing simple analytical techniques for solving differential equation. Okay, if it is in the complex form, then you can go for the numerical solution, and then numerical solution you can use MATLAB for that. Okay, so you are already conversant with using MATLAB to solve ordinary differential equations, so you will use the same fundamentals and solve these equations. Now what do you need for solving these equations? In addition to these equations, you will need initial conditions. Okay, so you need to specify what are the initial conditions, and you need to specify the input tau. Okay, what is the input that you are applying? So those two things along with the equations will give you the solutions. What is the trajectory or time history of the generalized coordinates? Okay, understand that? So for 2R manipulator, we saw the whole procedure yesterday. Okay, so we finally ended up in this equation. For this equation, this is a D matrix, and this is a C matrix. Now you can notice here that this D matrix, this term and this term, they are equal. Okay, so in general, for all the D matrices that you get for all the robotic manipulators, your matrix will be symmetric. Okay, that is a property of this D matrix when you get it from Lagrange formulation. Okay, another thing, we'll see some more properties, and then we'll generalize those properties also. So C matrix has this kind of a form, where H in the C matrix is given by this expression, and these G1 and G2, they are gravity terms in this vector. So this G1 and G2 are gravity terms in this bold G vector. Okay, so now next we will see one more property. Okay, now what if we differentiate this D dot D and find out what is D dot? Okay, so this is our D matrix, and we find out D dot now. Okay, when doing the differentiation, only this term will contribute, all other terms are constant. So this is m2 2l1 c2, and cosine is derivative is sine q2 and q2 dot. Okay. Likewise, in all the terms we will take a derivative and we will get this d dot matrix. Okay. Now if we use the same h as we defined in the previous case, we get this d dot matrix to be of this form. Okay. Now do you see any kind of a similarity between this d dot matrix and C matrix? Just see what is your expression for C matrix. This was a C matrix, and your d dot matrix is this. Okay. So you will find this matrix C and D. If you just multiply C with 2 and subtract it from d dot, so you will get d dot minus 2c. You will find that these diagonal elements are 0, and the elements which are off diagonal, they are negative of each other, like aij will be equal to minus aji. Okay. So you know what is this property of the matrix? Skew symmetry. This is a skew symmetry property of the matrix, and it's very important property for all the robotic manipulators. Okay. From the control perspective, this has a lot of repercussion. So you should have very firm understanding of this part, so as to use this for the development of control later on. Okay. So this is a skew symmetry property, and then in combination with this skew symmetry, if we see now a quadratic, like if you take a skew symmetric matrix, okay, and then you form a quadratic out of that matrix by multiplying by q dot transpose, and again multiplying prefix to the matrix q dot transpose, and after the matrix expression. So that is something like you take this matrix C. Oh, I cannot write over here. So basically you take the matrix C, multiply on the one side, on this side by q dot, and on this side by q dot. Here it will be q dot transpose, and here it will be q dot. Okay. Rather for this matrix d dot minus 2c. So you take this d dot minus 2c matrix, on this side you multiply by q dot transpose, on this side you multiply by q dot, and then you see what is the expression that you get. Okay. You will find that that will be 0. So that is a property. If you form a quadratic by multiplying these matrices by vectors, then you will end up with the 0. Okay. So quadratic expression for skew symmetric matrices is null, is 0. Okay. So that is a property that is used in many of the control developments. Okay. Control developments, control stability proofs, everywhere these properties of a lot of use. So we will see that in the later, like when we talk in detail about robot control, we will see how to make use of this property. But before that, we need to develop our understanding regarding some fundamentals of control. Okay. So that understanding will generate now. So this property first will generalize, and then we'll use it for control. Okay. And then we'll see, first we'll generalize this result. First we'll generalize this result, and then we'll go for some fundamentals about control. Okay. So to generalize these results, we have this theorem. You define this matrix n, which is d dot minus 2c, then n is q symmetric matrix. So component njk will be equal to minus nkj. So for that, to prove this property, we will use this C matrix, and this D will differentiate in this fashion. Each element will be differentiated like this. Okay. And then now if you take d dot minus 2c, you see what is happening here for this matrix expression. So these terms will get cancelled out and you will end up with this final expression. Okay. So you see, observe carefully this expression. Suppose now we put in place of k and j, you just put j and k and see what is the expression that you get. So you will find, if you replace this k and j, you will get njk is equal to minus nkj. Do you see that? So we have generalized this property in general for n-link robot manipulator. So all the manipulators whose expressions like the equations of motion are derived from the Lagrange formulation, they will all have this property. Okay. And then this property will be used, as I said earlier, in the control. In general, the nonlinear control of the robot. Okay. So now we'll stop here for the dynamics part of it, and then we'll see first some of the fundamentals of control. Okay. And these fundamentals of control, then later on we'll develop on them to again come back to this property and talk more about robot control. Okay. But first you need to have firm understanding what is meant by control, what are the different things that go in the control. So let us see what we are going to see in this robot control introduction. First we will see what is control configuration, typical control configuration. Then various types of controller. I will give you some brief idea about what all type of controllers are available. Okay. And then there are many issues in controller design and analysis. Those issues we will touch upon, some of those issues. So you have this background of control developed in your mind, and then you can use it later when we talk in detail about robot control, a nonlinear robot control. You can see in from this perspective, like this fundamental background perspective, and then you will get better understanding about how to implement, how to select controllers and things like that. Okay. So we'll also see some control implementation issues, and then we'll conclude the lecture. Okay. So controller forms an important element of robot manipulator. It's like a brain of a robot. So whatever sophisticated task robot performs, okay, that task, like the controller has to be designed to carry out that particular task. Okay. So controller is designed in a very sophisticated manner for all the high performance task robots. It's like a brain of a robot, and it really gives that intelligence to the robot. So suppose you design controller wisely, then it will improve the performance of robot. And if you have no fundamental understanding about the control and you are not designing a control properly, then it may hamper the performance of the robot. Okay. It may badly affect the performance. Whatever task you want to achieve out of the robots, may not be achieved. So it is very important that you think about the controller in the depth for any type of robot that you design or you use. Okay. There are other issues like how do I design controller now? Okay, there is a huge knowledge base about this. How one can design a controller. Okay. To give you just an idea, in general this control theory has been developed over the years so much. I mean there are so many different varieties of controllers available in the literature. And just to give you current status, current research status, like there are two important conferences that are held internationally, very important control conferences. One is Conference on Decision and Control, conference on it is called CDC, Conference on Decision and Control. Another is ACC, American Control Conference. Okay, so there are a lot of papers, like can you imagine number how many papers are published every year in these conferences? They are in the range of about 2000 to 2500. So there are 2000 to 2500 new research papers, okay, which are referred, I mean that which are like gone through scrutiny, okay, gone through like a rigorous review. They are published in these conferences. So there is so much of new literature on control is being generated every year. Okay, so this control is really a huge vast area, and in this course we will not be able to cover it in entire gist. So for robot control we will give you some like fundamental understanding and the directions where you should go for more sophisticated kind of a control. Okay, so it's really a huge knowledge base. Okay. Now another important issue is regarding the implementation of controller on your manipulator. How do you implement controller on your manipulator? Okay, so we'll touch upon these issues in a little bit fashion, and then I'll like later on when we talk more about robot control in specific, that time I'll give you some more hints how to implement control. Okay. So this is a typical control configuration for the robot manipulator. Okay, I mean this part you can say it is a general control configuration for any dynamical system, but typically each axis of the robot will have this part. Okay, so you have this lower level controller which is actually controlling the actuators. The sensors can be giving feedback from either actuator or actual robot manipulator. Okay, so it can be either of these two. And then you have the higher level control. Now this higher level control has to generate some commands and then implement it to give it to the lower level controller. Okay, and then this higher level controller can be operating many such axes at a time. Okay, so it has to coordinate between the different axes of the robots. Okay, say for example typically robot will have like many joints. Okay, so all these joints need to be coordinated with each other, and that coordination task is done by the higher level control. Okay. Now what are the design issues in the controller? First is the stability. So controller should be stable. I mean whatever controller you design, it should be stable, both in the numerical implementation and in actual performance for the robot. Okay, then what is the performance of the controller? So it is high performance controller or low performance controller, like that. You can have various levels of performance that can be given by different types of controllers. Okay, so depending upon your application needs, you have to select appropriate control strategy to suit your performance requirements. Okay, another very important issue, usually when you study the control theory, this issue is neglected. I mean, people don't give enough attention to this part, which is how much is the energy that I need to put in the system to achieve the level of performance that I am getting. Okay, so it is like a balance. Like you have on one side your performance, you want a better and better performance, and on the other side you have limitations on the energy that you can give. Okay, so your controllers are always optimally balanced on these two issues, depending upon the needs of the particular application task that we are talking about. Okay, so this issue, energy required to achieve very high performance, is very important issue. So kindly you pay attention to this. Like whenever you design a controller, first simulate and see what is a control input that you require to achieve whatever quality of output that you are getting out of your robotic system. Okay. Then there are issues regarding implementation. So you can implement controllers in analog domain by using electronic circuits, or in the digital domain by using microprocessor or computer. Most of the modern robots, you will find that control implementation is done with this way. You either use computer or you use microprocessor. And there are in general you will find many microprocessors used in a typical robot. Okay, for each axis you will find there is a separate microcontroller used. Okay. Next we will see what are the different types of controllers available. Okay, there are several types. As I mentioned, it is a very vast area, so I have listed only a few of them here. Okay, first and foremost important is this PID controls. Okay, PI or any combination of these, PI, PD, you can use it for controlling the robot. Now these are traditional, used in many industries. Okay, and the important thing here is that, like these controllers, when you will use these controllers, basically whenever your task needs are not very high performance, or you want to move it very slowly, like you have to pick and place objects very slowly, or you have to do the trajectory tracking very slowly. In those cases you will use this kind of a control. Okay, so these controllers, PID controllers, they will not give very high performance. Okay, but they will cover up your needs. Okay. Then next is nonlinear control. Nonlinear control is again very vast field and is actually developing. It has not been saturated. Like there are lot many new things coming up in this field. Okay, and you see all your equations of the robots that you get. Say for example, we saw the two-link manipulator. Those two-link manipulator equations were in the nonlinear form. Okay, for the nonlinear form of the equations, in general, you will require nonlinear controllers. Okay, so whatever we will study controllers mainly will be in these two classes, like proportional, traditional way we will see, and we will see some high performance nonlinear controllers. Okay, there are other types of controllers which are robust control, adaptive control, neural network control, fuzzy logic control, then optimal control. These are various different types of controllers that are available, and they can be used for robotic applications also. But Unfortunately, because of the time restriction, we will not be able to get into details of these controllers. They are more modern. Some more modern passivity based controllers are also there. Then there are controllers based on the Lie brackets, Lie derivatives that are available. I mean, you see in the latest literature, they will be of that kind. Okay, but unfortunately, we will not have time to go in the details of all of these controllers. So we will give you some fundamental understanding about these two classes, like this PID class and the nonlinear class, and then we'll have these other things for your own study. Okay. Now, what are the design steps that you will follow to design a controller? First, very important step is modeling, and we have seen this modeling of the robot, basically getting a mathematical representation for the robot dynamics in the differential equation form most of the cases. Now, this we have seen already by using Lagrange formulation in the last class. Okay, and we have also outlined this procedure in this class to get mathematical representation of a robotic manipulator. Okay, the second thing you see is selecting the control strategy. Now, here is where like you have to put in a lot of effort. I mean, you have to do first, you have to have first a good understanding of the dynamics. So, carry out some simulations, understand the dynamics of your robot. Okay, step response or some kind of a response you see, how for a given input how the robot responds, and then based on that you can say like what kind of a controllers you will have to select. Okay, and then you carry out this selection of a controller step. Now, next is once you select a controller, then what you have to do is like controller parameters. There are many controller parameters. You have to select them, and then that selection or tuning will be based on again the performance requirements. How much performance you want out of your system and how much energy you can give. These two constraints will always be there. Like anytime you select or make a choices, these are the two criteria you will use to make those choices. Okay, and then you will carry out, once you select the control strategy, finally you will carry out simulation using this strategy and do the experimental implementation to test it. Okay, so these are the typical steps we will follow in the control design. Okay, next we will study what are the different ways of mathematical representation. We have seen one way for the robotic manipulators. Okay, that way was by using your Lagrange formulation and getting the differential equation, ordinary differential equation governing your robot manipulator dynamics. Okay, but there are some other representations also you should be aware of. I mean, they will not be directly useful for the robotic manipulator cases, but you should be aware of that there are some other mathematical representations mainly for the linear systems. Okay, one is this state space form, as you see in the slide. This is a state space form. Basically, you reduce the order by changing the variables and put in the matrix form. So, reduce the order of each equation, like so you in the robot we got second order differential equation for each joint. Okay, so here you will reduce that second order differential equation to the first order by introducing some new variable. Okay, and then you can put that equation in this form: x dot is equal to ax plus bu and y is equal to cx plus du. So, this is called as a state space form, and then this form, in this form, this A matrix, B matrix, C and D matrix, they are characterizing this form, and these matrices are constants for linear systems. Okay, so using this state space form, there are a lot of control tools that have been developed. Okay, and then again, like when you say this A, B, C, D constants are these matrices are constant matrices, then it is you are talking about a linear system. So the tools that have been developed in the literature, they are for the linear systems only. Okay, so if you have a linear system, or if in some sense, like for simple robotic system, you can represent it in a linear fashion or approximate it in a linear fashion, then you can probably use the tools which are in the state space theory. Okay, then you see the next form is a transfer function form. Okay, so the transfer function has typically this kind of a form. It is in the Laplace domain. So it will be like a numerator over denominator polynomial for the Laplace, and then this Gs will be basically the Laplace transform of the output divided by Laplace transform of the input. Okay, so you have to represent the equations, like you have to take the first the Laplace transform of the differential equation, and then you have to separate out output and input and take their ratio. Okay, name it as a transfer function and find out this numerator and denominator polynomials. This is how you will go to find out. This is how you will proceed to find out your transfer function. Okay, this transfer function analysis is mostly in most of the robots, like you will not find that this kind of analysis you need to do. I mean, you will need to do this kind of analysis mainly for the actuator dynamics of the robot. So because actuator dynamics, you can say that it is in a linear domain. Okay, but again, it is not independent of your robot itself. So if you are taking into consideration the coupling terms because of your robot manipulator joined with your actuator, then it doesn't really become remain a linear domain. So, but you should have this understanding. Okay, we'll see some details when we talk about PID type of control, how we can represent PID in the Laplace domain and use it for robotic manipulator. Okay, now there are many important notions in stability, I mean in analysis. Okay, there are many important notions in analysis of control. The first, foremost important is a stability. How do you define stability? One of the ways people define is bounded input leading to bounded output. Like if you have a bounded input given to the system, a finite input which is given to the system, then it produces a finite output. That is one of the ways. There are many other notions like asymptotic stability, exponential stability. So these exponential stability is basically for the linear system. All the linear systems, whether it is stable, when you say it is stable, when you say a linear system is stable, it can be only exponentially stable. There is no other notion for linear systems. But when you go in the nonlinear domain, then you have these other notions of the stability possible. Say for example, asymptotic stability. It means that your output goes to your equilibrium, okay, in asymptotic fashion, meaning output goes to equilibrium as time t tends to infinity. That is kind of a notion that we are talking about here. Okay. Then exponential stability is output goes to the equilibrium in an exponential fashion. There is no restriction in asymptotic stability for in what fashion it goes, but it goes to infinity as time t it goes to 0 or equilibrium as time t tends to infinity, but in the exponential it will go to 0 in the exponential fashion. Okay, so that is the difference between these two notions. Then there is a notion called controllability. So for that, like say you have state, see I have plotted here q1 and q2 space, which is like a coordinate space. Okay, so this is a state kind of a space. I am just using just 2 coordinates here, but in general for robotic manipulator there may be number of such coordinates, and you want to move from this point to any other point in this space. Okay, so controllability refers to whether the robot can be taken from this point to this point in the finite amount of time. Okay, so we should be able to take robot from one state to other state in a finite amount of time. Then we can say that the robot is controllable. Now, in case of linear systems, there are conditions on this ABCD matrices for controllability. There is another notion called observability, which we will see next. Okay, observability basically refers to whether whatever sensors we are using, are they sufficient for our control application, control purpose. So observability answers this question. Okay, so whether whatever feedback we are taking, are we able to construct the state out of that feedback completely? Okay, and again there are conditions on matrices ABCD, as you see, for this observability. And then there are several standard tools available in MATLAB for this analysis, either in the linear domain or in the nonlinear domain. Okay, next we will see how classical controller will look like. Okay, we will typically have this plant which is in the linear domain. Then there is this actuator, sensor and controller. Now this is the expression for PID controller in the Laplace form. Okay, these PID controllers are used widely for both linear and nonlinear systems. Then they may not always lead to the stabilizing controller, because you see this integral action here is in some sense destabilizing the system. Okay, the derivative action is kind of you are introducing like more damping into the system. In integral action you are introducing one more pole near 0 in the S plane. We will talk about this thing little bit more when we actually see for robot how to use these PD controllers, but you just remember that the integral action will have a destabilizing effect. Okay, and they are used, integral action is used when you want that the steady state error to go to 0. Okay, you don't want any steady state error when it reaches some final position. In that case you use integral action. Okay, and then if you want to kill any oscillations like robot link vibrating and settling down, you want it directly to go to final position. In that case you use derivative control action. Okay, so just remember these things. Now what are the techniques that are available for doing these analysis? So this slide lists all the techniques, most of the techniques actually. to do the robot analysis. The techniques in this first class, they are classical techniques, control techniques. Okay, this is a root locus, Bode plot, Nyquist plot. Okay, these are all graphical methods for linear systems. You cannot talk about root locus for nonlinear system. So typically, n degree of freedom manipulator, you should not say what is its root locus. I mean, that's not a right question to ask, because it is in general a nonlinear system, and you cannot talk about root locus for nonlinear system. Okay. Then other tools in the nonlinear domain, you see this Lyapunov method, which we'll use for our control development. So we'll go through some fundamentals about this Lyapunov method. Then there are singular perturbation tools. Okay. Then feedback linearization. These are all nonlinear tools, or tools in the nonlinear domain. We'll not be able to have like enough time to go through all these tools, but you should be aware that such tools exist. Okay. In case the tools that we have seen are not sufficient for you for your application of robot, then you should be going for the other tools. So you have to study them by yourself. They will not be covered in this course. Okay. Next, we'll see some fundamentals of control implementation. So in the control implementation in the analog domain is basically using electronic circuits, as I said earlier. And then in the digital domain, they are using computers or microcontrollers. In digital domain, these sensors and actuators are also used, which are in the analog domain. Okay. So sensors and actuators signals, they are in the analog domain. You are processing your control in the digital domain. Okay. So you need this conversion to be done from analog to digital domain. When you move from sensors to your controller, you use analog to digital domain converter, and when you use from your controller to your actuator, okay, that time you use digital to analog converter. Okay. Now what are the issues in digital control implementation? Let us see them one by one. First is a sampling time. Okay. So we'll talk about this little bit in detail when we actually come to control implementation in the later classes. But you probably would have observed this when you see movie. Sometimes, like if there is a cart which is going in the movie, its wheels, they appear rotating in the opposite direction to the direction of the movement of the cart. Okay, that is a thing, that is a problem because of the sampling issues. Okay, it is not enough fast sampling that has been done, so that like it appears like the motion is distorted. So like that your signals also will get distorted if you don't do enough fast sampling of the signals. Okay. Then effect on the system due to sampling. This is again a very important issue. Like because of this sampling, what is its effect on the actual robotic system? So if you are, the best way is like sample with the right speed, so that you don't get into the effects, the bad effects of sampling on the system. Okay. Then you need filters to filter out your sensor signals. Typically your sensor signal will have a noise, so you have to filter out this noise from the sensor signal. So you have to use these filters either in the analog domain or in the digital domain. Then another issue is speed of computation. Like whatever microprocessor you are using, is it sufficient to compute your control law in a given sampling time? Okay. So in the fixed sampling time, your control computation should be over for that particular time period. Okay. These are all the issues when you come to practical implementation. You have to deal with these issues. If it is not sufficient, then probably you have to go for a high speed microprocessor to achieve the same task with the same controller. Okay, or else change the controller to some lower order or less complex controller so that you can implement it easily with the whatever available hardware you have. Okay, then speed of A to D and D to A conversions. This is not very important issue. It will be usually in much higher, much faster speed the conversion will happen as compared to the speed at which you are moving your manipulators. Okay, so this time usually we are talking about in some microseconds of conversion time. Okay, then number of sensors and actuators. So if you have number of sensors and actuators, like your amount of processing is going to increase, filtering and all other things. Okay, and then this noise, as I mentioned, and finally the most important is the cost. Okay, you have to see what cost you are incurring to get this performance. Okay, without consideration of cost, nothing will be accepted. You have to give good consideration to the cost. Okay, if it is at a research level, when you are carrying out some application, then you can like slightly be flexible about the cost issue. But when it comes to the industrial application, then the cost issue assumes a lot of weightage. Okay, so this is a kind of a scheme that you see in the slide for the implementation in the digital domain. Here you can have these two schemes possible, like you use computer or you use microcontroller, and then other things remain the same. And then microcontroller will have usually built-in A to D. Okay. Okay, this is a little picture about a movie of this rhino robot performing some task, but in the interest of time, maybe we can look at it in some later classes. Okay. So what we have seen today is basically overview of controllers, then several design steps that you need to follow for development of controller, different types of controllers we have looked at, and then some issues in the implementation of control, basically regarding two controller implementations, which is the analog and digital domain, and some issues regarding digital domain implementation of control. Okay, so it is very important to have the fundamental understanding of the controller right for any robotic application to be realized in practice. Okay, so we'll stop here for this class, and in the next class we will continue our discussion with the control. Okay, thank you.